Thanks for inviting me, and thanks everyone for coming. So I'm going to talk about list decodability of randomly punctured codes, and in particular I'm going to talk about the list decodability of Reedsolomon codes. And this is joint work with Atri Rudra at SUNY Buffalo. Okay, so here's a brief outline of what I'm going to talk about. So first I'll just set up some notation, define sort of the coding theory and list decoding things that I'll be talking about. I'll define Reedsolomon codes. Then I'll state some results. So the punchline, so for those of you who already know the lingo, is that there exist Reedsolomon codes which are list decodable beyond the Johnson bound. So that's what we're going to be going for. And then time I'll talk a little bit about the proof. I'm actually going to give two proofs. So one, which will be more general from this recent work with Atri, I'm going to just sort of kind of wave my hands at because it's a little technical. And then another one, which is much more simple but much less general. I'll give a second proof, which hopefully is easy enough that I can give it in its entirety in maybe 10 minutes. So that's about it. So let me start with some definitions from coding theory. Okay, so in coding theory, so I'm going to be talking about error-correcting codes. And for me, a code is going to be just a subset of fq to the n. And there are a couple of things that we care about for a code. We care about the distance and the rate. So here's my little picture of a code. All of these little red dots are elements of my set. And I'm going to call them code words. And the distance of the code, the minimum distance of the code, is the minimum distance between any pair of code words. And here distance is relative Hamming distance, so the fraction of the n symbols in which they disagree. And I'm also going to care about the rate of this code, which measures sort of how many red dots I can have as a function of n. And one reason we care about error-correcting codes is for communication. So I've got Alice and Bob, and they want to use this code to communicate, right? So what are they going to do? They're going to agree on this code beforehand, agree on an encoding scheme, which will map messages to code words. And so, maybe Alice wants to say, attack at dawn to Bob. And so she's going to pick this code word and send it to him. And the model of the communication is that there's going to be some errors introduced. And my notation is that the error rate is going to be rho. So a rho fraction of the symbols that Bob sees are going to be corrupted. And if they have a good code with good distance, which is more than twice the error rate, then they can communicate, right? So if Alice wants to say attack at dawn, she sends Bob this code word. It gets perturbed a little bit. He sees this corrupted code word W. And if the distance of the code is big enough, he knows that there's a unique code word to which that message corresponds, or to which his received word corresponds, and he can, sort of prepare accordingly. He knows what Alice meant to say. Okay. So that's coding theory in a nutshell. But there's a problem here, or maybe not a problem, but sort of a fundamental limitation of the unique decoding paradigm, which is that when rho, the error rate, is bigger than half the distance of the code, there's not much that Bob can do here. So for example, if Bob sees this code word here, which was, maybe it started life as, or this corrupted code word here, which maybe started life as one of those 4 code words, and it got corrupted by more than half the distance, Bob really can't tell which of these 4 Alice meant to say. And there's really not much that he can do about this. So one thing we could do, we could throw up our hands and say, too bad, let's just say that the error rate never gets that big, or we could try to find a relaxation that allows us to have the error rate that big. And so that's where list decoding comes in. So the idea is that even though Bob doesn't know which one of those 4 code words Alice meant to send, he knows maybe that she meant to send at least one of those 4. Like this one is right out. She didn't mean to say that. And so now Bob he can at least say something. He said he can recover a short list of possible things that Alice meant to say, even when the error rate is much larger. So more formally, I'm going to say that the code is list decodable if it allows Bob to do this. So I say that it's rho L list decodable if for any received word W that Bob might see, the number of code words within radius rho of that received word is small, no bigger than L. And for the rest of the talk, I'm going to think of L as being like polynomial in everything in sight. And when I forget to mention L and I just say something is list decodable, I mean list decodable with list size is polynomial in everything in sight. But not N, right. List decodable in 1 over epsilon, so, which I haven't defined yet. So yeah. Reasonable sized L. So just here's the picture. So this for this code here is row 4 list decodable, because wherever I put this green dot W, there's at most 4 code words that live in that dot, whereas this code is not very list decodable. If I put W right in the center, there are lots of code words contained in a bowl. Okay. So we want something more like this. Okay, so list decodable codes have been around for a long time. They were introduced by Elias and Wozencraft in the 50s. Since then, they have lots of applications, not just for Alice and Bob and their communication, but also to complexity theory, pseudo-randomness. They're sort of deeply connected to extractors and expanders and stuff like this. It's a very nice combinatorial object. And one question we can ask is, well, how well can Alice and Bob do at this game? Like, what's the best code we can hope for? Right? Maybe it's the case that all codes kind of look like the picture that was over here, where all the red dots were kind of clustered around in a circle, and they don't really get anything from this. And it turns out, fortunately, that that's not the case. The picture can look much more like the one that I had over there, where all the code words are sort of spread out. And so the parameter regime that I'm going to be interested in for the rest of the talk is the one where the error rate is 1 minus epsilon. So think of the alphabet size as being very large. So it's over FQ. Q is really big. And I want error rate that approaches 1. So nearly all of the symbols could be corrupted. And the parameter regime that I'm going to look for is I want some positive rate, let's say rate epsilon of the code, with list sizes polynomial in 1 over epsilon. And it's not hard to see that this is sort of the best you can do information theoretically. Right? If I want to send, sort of morally speaking with some hand waving, if I want to send an epsilon information, I can corrupt at most a 1 minus epsilon fraction. And so that's about the best I could hope to do, and it turns out that you can do it. So if I take a random code, so plunk down all those red dots completely at random, that will achieve this for you. And so that's called the list decoding capacity theorem. And so just to compare, for unique decoding, the error rate needed to be less than 1 minus epsilon over 2. So this allows us to effectively double the errors, so to handle error rates approaching 1. OK, so that's list decoding. Are there any questions about list decoding? OK. So now this talk is about list decoding of Reedsolomon codes primarily. So let me tell you what Reedsolomon codes are. Or probably I don't need to define them for this audience, but I'll have a slide anyway. So in Reedsolomon codes, Alice has some message, m, of length k. She's going to think of her message as a polynomial by just treating each of her symbols as coefficients of a polynomial. And the code word that corresponds to this message is just going to be the evaluations of that polynomial over a bunch of points in a finite field. And my bunch of points, alpha 1 through alpha n, are called the evaluation points. So often it's the case that I would take the whole field, but for us it's going to be important that we get to choose the evaluation points. So the rate of this code is k over n. Alice wants to send k symbols. She ends up sending n symbols. And it's not to see that the distance is 1 minus k minus 1 over n, simply because any 2 polynomials of degree k minus 1 can agree in at most k minus 1 places. Okay. So Reedsolomon codes are old and celebrated and have been studied for a very long time and are used all over the place. And in particular, the list decodability of Reedsolomon codes have been studied a lot. So what do we know about the list decodability of Reedsolomon codes? So we know one existential thing we know is called the Johnson bound. So this is a theorem that holds for all codes, not just Reedsolomon codes. But it says basically that if you have good distance, if a code has good distance, then it has good list decodability. And this seems intuitively like it should be right. If all the code words are spread out, then not too many of them can be contained in a single ball of radius rho. And you can make that intuition quantitative. And when you plug in the distances and the rates of Reedsolomon codes, what you get is that a Reedsolomon code of rate about epsilon squared can handle error rate about 1 minus epsilon. And so this is sort of the parameter regime we were after. And the remarkable thing about Reedsolomon codes for list decoding is this great work by Gaussian and Sudan in the late 90s, which shows that you can actually list decode Reedsolomon codes up to the Johnson bound efficiently. And this has been very important and has sparked a lot of work on list decoding in the past decade or so. Okay. But so this is perhaps not quite as nice as we would hope, right? So I said, this is awesome, but there's a gap here with this epsilon squared. So here's the list decoding capacity theorem, which I showed you before, which says that if I want to handle error rate like 1 minus epsilon, so nearly all of the symbols are corrupted, I would like my code to have rate about epsilon. That's the information theoretic limit. And the Johnson bound here says epsilon squared. And when epsilon is small, then epsilon squared is quite a bit smaller than epsilon. So this is not the right asymptotics on epsilon. And so we might ask, well, can we close this gap? Okay. And in fact, lots of people have asked this. Can I get a rate of epsilon with error rate 1 minus epsilon efficiently? And so for Reedsolomon codes, you can get rate epsilon squared. And since then, there's been a whole lot of other codes which you can get rate epsilon. So starting with Parvaresh and Vardy gave the first codes which could efficiently beat the Johnson bound. And then Gaussian and Rudra showed that something related to Reedsolomon codes, but not actually Reedsolomon codes, called folded Reedsolomon codes, can get the optimal rate with this error rate. And Swastik showed that multiplicity codes can do this as well. And we now know sort of several families of explicit codes which can sort of get the best achievable rate error trade-off. But one thing to notice about this list is that none of these actually include Reedsolomon codes themselves. Most of these are variants on Reedsolomon codes. And so the motivating question where we started our work is, well, are there Reedsolomon codes which can be list-decoded beyond the Johnson bound? And so this was first asked by Gaussian and Sudan in their work, and it's been formulated a bunch since then. Whoops. And there's a couple of reasons. This is a couple of reasons why I care about this question. So one is that Reedsolomon codes are very well studied. They're sort of arguably one of the most studied families of codes that we know about. And the fact that we don't really understand their list decoding behavior is not good. Another reason is potential complexity theory applications. So like I said, there's relationships between list decoding, especially in this 1 minus epsilon parameter regime, to pseudo-randomness, complexity theory, things like that. And then the third reason why it might be interesting to study this question is more of a philosophical one. Sort of the Johnson bound, this epsilon squared barrier, is kind of a natural bound that comes up a lot in coding theory. It's interesting to understand what structure or lack of structure you might need to get beyond it. And people have studied this question, and actually there's been evidence going both ways. So some reasons to think that the answer should be yes. Well, Reedsolomon codes are really nice. They're optimal for a lot of things. Why not here, too? Another reason is that all those constructions that I showed you, most of them, or many of them, are variants on Reedsolomon codes, so folded Reedsolomon codes or Reedsolomon codes along with some derivatives information, stuff like that. So those are two reasons to think that maybe the answer is yes, there are Reedsolomon codes which can be list-decoded beyond the Johnson bound. There's also been some evidence against it. So one major piece of evidence is if I replace are there Reedsolomon codes with are all Reedsolomon codes list-decodable beyond the Johnson bound? The answer is no. So that is, there exist Reedsolomon codes, by which I mean there exist ways to pick those evaluation points, for which the answer is no. So I can't improve the rate if I take, for example, all of the evaluation points, or more generally, if your evaluation points contain some nice algebraic structure. You sort of need this epsilon squared bottleneck or something very close to it. And another evidence pointing against it is that the Johnson bound is the right answer for the list recovery problem, which is related to list decoding. Okay. So in this talk, I will tell you that the answer is, in fact, yes. So there are Reedsolomon codes which are list decodable beyond the Johnson bound. And actually, our result tells us more. It says that actually most Reedsolomon codes are list decodable beyond the Johnson bound, in the sense that when I take random evaluation points, this will work with very high probability. We'll get not only beyond the Johnson bound, but actually very close to this linear dependence on epsilon that we're after. And moreover, the techniques that we use are more general. So in particular, we get some applications for random linear codes, list decodability of random linear codes, which were not known, and more generally to randomly punctured codes, hence the title of the talk. And I'll explain what that means in a minute. OK, so that's the intro section. Are there any questions before I throw up a theorem? OK, I'll throw up a theorem. So here's the result for Reedsolomon codes that I was just waving my hands about. So if you pick parameters q and k and epsilon, so that holds, that q is large enough, and for Reedsolomon codes, we think of q as being very large, so this is fine. and let C be the Reedsolomon code over FQ, where I choose n evaluation points uniformly at random from FQ. And how do I choose n, the number of evaluation points? I pick it so that the rate is like this. So this is kind of an ugly expression. So the thing that I would like to highlight is that there's an epsilon here, not an epsilon squared. And I'll come back and talk about this log junk in a minute, which should not be there. Right, so ignoring log junk, the rate can be like epsilon. And then with high probability, C is list decodable up to error rate 1 minus epsilon with list size is linear and 1 over epsilon. So that's the theorem. There is no efficient decoding. And actually, there's evidence that indicates that efficiently list decoding Reedsolomon codes significantly beyond the Johnson bound is as hard as discrete log over some fields. So probably, I think so. Yeah, so what's the, I'll get the reference for you afterwards. I should have that on top of my head. Cheng and Wan, yeah, okay, thanks. Yeah, yeah, so over certain fields. Right, so there's evidence that probably we can't have an efficient algorithm. Yeah. Randomly with replacement. Yeah, so some points could be equal. I think, yeah, so it doesn't really matter. That's going to be convenient for our proof to have the independence, but if you want to choose a random set at n of size n without replacement, that should work too. Any other questions about the? Oh, yes, it does work. And in fact, that's the statement that I'll prove. Right, I mean, that's case is kind of wasteful. You could just throw out those symbols, but that's how the proof works. Yeah. Okay, so I just want to briefly touch on this log junk. This would be a really cool theorem to get something linear in epsilon. It would be even cooler if the constant were right, but I'm not even going to hope for something that cool. This log junk is suboptimal in two ways. So this log to the 5th 1 over epsilon is, you know, obnoxious, and it shouldn't be there. And then this log q is actually a bit more than obnoxious. So that's you know, I think that's a real downside, because for Reedsolomon codes, we often think of q as being really, really large. Right, right. Right, so if it's polynomial in epsilon, that's fine. Sometimes you might want to think of it as being exponential in 1 over epsilon, in which case that's bad. Yeah, so there is a large parameter regime in which case this is really beyond the Johnson bound. But in particular, it means that if epsilon is constant, then this is not constant. So epsilon needs to be slightly subconstant for my punchline list decoding Reedsolomon codes beyond the Johnson bound to work. But allowing slight dependence allowing slightly subconstant epsilon, this is sort of basically what we would hope for. So that's the one caveat, is this log q is kind of messing stuff up. Okay. There any other questions about the statement? Okay, so let me state some generalizations. So actually, what we prove is a much more general result about randomly punctured codes. So what is that? So if I start with a code, so here's my cartoon of a code. Each of these guys is a code word. Each of them has length n naught. So I start with some code c naught. And it's well list decodable in the sense that, well, I'll define precisely the sense later, but let's say that it means that it has, you know, not too many code words contained within any ball. But the rate is not good. So for example, think of the Reedsolomon code with all of the evaluation points. So it is list decodable up to the Johnson bound, the rate's not good. And then choose n random positions with replacement or without replacement. I'm going to wave my hands out. The distinction doesn't really matter. So choose n random positions and throw out the rest, and just keep those n positions. And so now what you have is a new code C. It has the same size, but a much shorter length. So the rate has improved. However, our theorem says that even though the rate has gotten much better, it has the same list decodability properties. And I'll make this more precise in a moment, but the way to think about it for Reedsolomon codes is I started with this big Reedsolomon code with all of the evaluation points, which was list decodable with bad rate, I improved the rate, and I still have my good list decodability properties. Yeah.
By doing this, if you take a code and choose random positions, you pretty much get that the relative distance is more or less preserved. So I'm wondering if there's any connection. You showed that the list decodability is preserved. Was there any connection to the fact that also the regular relative distance is preserved well when you do this?
So for Reedsolomon codes, so we can think about what happens to the distance.
The relative distance is true for every code multilinear.
You mean that the relative distance is approximately preserved? But that's not true for Reedsolomon codes, right? Because
you have to keep the parameters carefully, of course.
right. So yeah. So in the parameter regime that I'm thinking of, for Reedsolomon codes, the distance stays the same and the length decreases, right? Because I'm still looking at all polynomials of length k. So in particular, the distance of my new code after I sort of take these n things is like 1 minus k over little n, and before it was 1 minus k over big N, or n naught. So in that case, the distance of the code has actually changed. Right.
It changes because it was very close to 1 here. What you were talking about is some constant distance. Here it's so close to 1 that it doesn't.
Yeah, right. So you're right that for different parameter regimes, I would expect the distance to stay the same.
We should think about you taking something like square root of the coordinates.
Yes, exactly. Something like square root of the coordinates. Yeah, or yeah, so if I start out, again, using the Reedsolomon case to just like give some concrete parameters, if I started out with k over epsilon squared coordinates, I would end up with k over epsilon coordinates, about, where k is the degree of the polynomials. So yeah, so something like square root is about right. Okay. So does that make kind of address your question? Maybe we can take offline sort of the exact distance ramifications. Yeah, but I think that is a really interesting question, is asking sort of how the distance and the list decodability change together when you do this operation. Okay, so that's the general hand-wavy picture. There's one other generalization which I should talk about, which is, well, what if Q is not really, really big? What if Q is medium-sized? Then that 1 minus epsilon is not the right answer anymore. It's not attainable. Instead, what I should be shooting for is something like 1 minus 1 over Q minus epsilon. That's sort of the limit that I could hope for. And the list decoding capacity theorem still holds, and it says that the rate that I should be shooting for instead of 1 minus epsilon should be more generally like 1 minus the Q area entropy of the error rate. That's the best I can hope for, information theoretically. And so what is that? If I have this rate, which is 1 minus h of Q of 1 minus 1 over Q minus epsilon, well, so there's the curve, and close to 1 minus 1 over Q kind of looks like this. And if you just do some mucking around with Taylor series, what you get is that, morally speaking, this rate that you're after should be like epsilon in the case when Q is very big. So that's the situation that I just talked about for Reedsolomon codes. Or if Q is kind of medium-sized or small compared to 1 over epsilon, then you should be hoping for something quadratic in epsilon with a constant that depends on Q, like this. Okay. Oh, sorry, H sub Q is the Q area entropy of rho here. So the Q area entropy is just a generalization of the binary entropy, but it turns out that this is the correct answer, the information theoretic limit for the rate. And yeah, so what I've plotted here is what this correct rate should be as a function of the error rate rho. And in particular, I'm interested in this little bit of curve down here where it's very close to 1 minus 1 over Q. Yeah, so, sorry, I didn't. Yes, the Q area entropy is, okay, I'm going to get it wrong, so someone should help me. Yeah, so it's log Q of Q minus 1 minus Q x minus. Is that right?
It's also the entropy of the distribution, which is
Okay, right. But yeah, that's right. Okay, and what I wrote down, is that correct? I always mess up the minus signs. People confirm? Okay, so something like that. Yeah, so that's the definition, or what you've all just said. Okay, so are there any more questions about this curve? Sorry, I went too fast. Yeah. The borderline is like 1 over epsilon, or maybe 1 over epsilon squared. So yeah, I mean, so the borderline is when this switches, basically. Yeah, and so when Q is like 1 over epsilon, then this starts being dominated by that. Anything else? Okay. And so, right, so our more general theorem holds for all Q and also for this sort of randomly puncturing setting. And here's the statement that we prove. So if you start with a code C0, that was my big code with bad rate, and it has good distance like 1 minus 1 over Q minus epsilon squared. And where does this distance come from? This is the distance where the Johnson bound is enough to say that it has list-decodability up to 1 minus 1 over Q minus epsilon. So you start with a code whose distance is good enough that the Johnson bound would apply, which means that it has suboptimal rate. And then you make the rate better. So choose n so that the rate, which is k over n, is something like this. And I'll compare that to what the right answer was in a minute, or actually I can compare it now. Right, so choose n so that the rate is something like this. And remember, the rate that we were shooting for was something like this here. And so this, again, there's the log to the 5th junk, which is unfortunate in both parameter regimes, and the log q junk, which is necessary in the small epsilon regime and unfortunate in the big, which is necessary in the small q regime and unfortunate in the big q regime. Is there? So this maybe morally kind of matches a little bit. And the punchline is that if you take C to be, right, if you take C to be a random puncturing, so take that picture where I keep enough of the points that the rate is like this, then the code that I get is list-decodable sort of up to the error rate that I would hope for with list sizes polynomial and 1 over epsilon. And here the polynomial is innocuous. It's either 1 over epsilon or 1 over epsilon squared as appropriate for the parameter regime. So we get basically the right answer there. If you start with a code with good, like, average radius list decodability and do this, so I'll come back to that question when I go over the proof, and I'll say exactly what we need. So you can start with something more general than distance, but for now I'm just going to state it with distance. And right, the reason I want to state it with distance is because then it sort of smells like a randomized Johnson bound, which is better than the Johnson bound in some sense. The Johnson bound says I start with a code with good distance, I get decent probability, I get decent list decodability. This says I start with a code with good distance, I do this weird random thing, and then with high probability I get good list decodability. So it's kind of like a structural statement like the Johnson bound, but kind of randomized. Okay. So let me just wave my hands about one other application of a theorem like this, which is to random linear codes. So a linear code is a code, so a subspace of fq to the n, which just forms a subspace of fq to the n. And a random linear code is a random subspace of fq to the n. Another way to think about a linear code is its encoding procedure. So Alice has this message x, she wants to send it to Bob, so she's going to encode it by multiplying it by a random matrix G. And Bob sees the output, which is this code word. And the code is the set of all such code words that you can get by multiplying by this random generator matrix. Right. Yes, right. So each entry of G is IID in FQ. Right. And this fits into the framework before of randomly punctured codes as follows. So right, exactly. So any linear code is a puncturing of the Hadamard code, which is to say that this generator matrix G has a bunch of independent columns, which I can think of as being drawn as being a puncturing of the generator matrix, which included all of the columns. So the 2 to the k, or sorry, q to the k by k. K.
Huge, I mean, for typical polynomial parameters, like throwing away pretty much everything.
Yep, yeah, throwing away pretty much everything. That's right. Yeah, so basically, yeah, but that is where we start, though. You start with the Hadamard code. I know it has good distance, even though, like you say, the rate is atrocious. So the block length is 2 to the k, rather than something polynomial k, and I throw away almost everything, and I can still get something good.
Applies with parameters. I mean, that's a simple German part of this, but with your proof, can you conclude from your proof that a random generating matrix is as good as it would be by a normal?
What do you mean normal proof? So I don't. A turn-off bound will not tell you that this is. A turn-off bound won't tell you that this is true.
Oh, for list decoding, it will not tell you that this.
Right.
Right. I was just talking about this.
Oh yeah, yeah.
It won't tell you.
Yeah, it's true.
Good.
Yeah. Yeah. So this would be. This is new. So actually here, let me throw up the obligatory big table of what we can tell about random linear codes. Right. So here's the answer we'd be hoping for. So this is what just a random code attains. So the rate is that sort of epsilon squared dependence with that constant on q that I had before. The list size is like 1 over epsilon squared. And until recently, the best that we knew for random linear codes, for the list decodability of random linear codes, you could either get good rate or good list size. So sort of standard classical techniques show that if you want to get the correct rate, you can do it with exponentially bad list sizes. So that's kind of a bummer. Or you can get the right list sizes with bad rate. So this is what the Johnson bound gets you if you just throw in, like you said, the distance argument that you get from a turn-off bound, which is correct for random linear codes. And so that gives you an epsilon to the 4th, and you'd like epsilon squared. And this was open for a long time. I guess it was maybe first formally asked by Elias in 1991 what the list decodability of random linear codes were. And so then more recently, there's been some progress. So Chiragshi, Gaussian, and Velinker have this really nice result where they show that you can keep the good list sizes and improve the rate nearly to optimal. So the dependence on epsilon is off by some log junk, and then the dependence on q is not quite right. And so the arguments that I'm going to tell you about today, so as a corollary of that big theorem that I said, we can get this result, which has the correct dependence on q, but even more log junk. Or I'll show you another argument where you can get the correct dependence on epsilon, but not the right dependence on q. And I don't know right now how to get both of them at the same time. But so far, this is the best known for random linear codes. Okay. Right, so are there any questions about the statements and stuff before I start giving an overview of the proofs? Okay, so like I said, I'm going to tell you about, I'm going to give you 2 proofs, but they both sort of fall in the same general outline. So the first statement is to pass to something called average radius list decodability, which is a little bit stronger than list decodability. And so this has been studied implicitly for a very long time. Explicitly, it's recently been studied by Guruswamy and Narayanan, have sort of a more coherent or cohesive view of it. But here's the definition. So let's recall the definition of list decodability in pictures. It says that if I have any L+1 points, then at least, and any ball of radius rho, then at least one of those points lies outside that ball. That's what list decodability means. I can't have L+1 points all contained within a ball. Okay. In contrast, average radius list decodability says that if I have any L+1 points, then their average distance from their center better be further than rho. So on average, they lie outside a ball. And so this is a stronger notion. The average distance to the center is always smaller than the maximum distance to the center. Right? So average radius list decodability implies list decodability. And so what I'm actually going to do is prove all those theorems that I just said, except with average radius list decodability instead. Okay. Are there any questions about, I didn't throw up an actual definition here, but do people understand what this means? I'm seeing some confused. If I choose, Not at random. So yeah. So so this is stronger. So take the worst possible list of size L plus 1. Take the worst possible point, which in this case is just going to be the center of those points, and ask that the average distance from that point is larger than rho. Okay. And so in contrast, normal list decodability says take L plus 1 points, take their center, the maximum distance better be larger than rho. Okay. And so now it's saying even stronger, not just the maximum better be larger than rho, but the average better be larger than rho. Okay. Everyone good? Okay, so what I'm actually going to show is this slightly stronger notion. Okay, so to understand this stronger notion, I'll draw a little cartoon. So here's, again, my cartoon of a code. So this is a code of length n, little n. It has size big N. And I guess the alphabet size is 4. It's blue, yellow, green, and red. So here's my code. And what does average radius list decodability mean? So it means that for every set lambda of size L plus 1, so here's a bunch of code words. So first I take the center of those code words. So what is that? So I can actually find that sort of symbol by symbol, right? So I want to find the received word W that would be the worst possible for Bob. So that agrees the most on average with this set. And so what do I put in the first symbol? Well, either yellow or green, right? So I'll put yellow. What do I put in the second symbol? Clearly green. Right, and so on. And so I can find this by just sort of taking the, element-wise majority. And now what does average radius list decodability means? It means that the average agreement between this guy that I just created and this set is not too big. So I'm going to write that like this. So the average distance I'm going to write as the sum of the pluralities of lambda, my set lambda. So I just made up this notation, so I'm going to spend a little while on it so that we internalize it, because I'm going to use it for the rest of the talk. So what do I mean by the plurality, the jth plurality of lambda? So here's a definition in symbols. It's the plurality in the jth row. So the first plurality is 2. There are 2 yellows. The second plurality is 5. There are 5 greens. And 2, there are 2 reds, and so on. So I've written those numbers down over there. So these are sort of row-wise pluralities. And what I'm interested in is the sum of these numbers. Or the average of these numbers. I want these to be small. Okay. All right. So does everyone internalize that? Because I just made it up. But yeah. And yeah.
Considering the best point for the center, for the infinity ball, not the average ball, it need not have been this point, right?
That's right. And that's why I passed to this average radius list decoding, because now I don't need to worry about it. I know that this is the worst point for average radius list decoding. Oh, yes, yes. So right, I want the average agreement to be small, the average distance to be large, right? But I'm much better at bounding things above than bounding things below. So I'm going to talk about it, or at least it makes more sense to me. So I'm going to talk about it this way. But yeah, you're right. So average agreement. Any other? Okay, so this is what we're aiming to show now. We're aiming to show that this random variable is small. And so the randomness here is over the choice of my code, the choice of the n symbols. And so, right, so to show that C is list decodable, it suffices to show with high probability the worst set lambda that I could take, this average agreement is small. Right, I want with high probability, I'm just going to show for this talk in expectation. That's enough. And then use Markov or something. So that's sort of what I want to control. And that will show average radius list decodability, which will show list decodability. Yes, yeah, yes, I'm going to pass to a Gaussian process. That's right. This is the only thing I know how to do. Yeah, so the basic plan goes in 2 steps. So the first step is to show that if I cheat and switch this expectation and this maximum, then I'm good. And I'm not going to talk about that. That sort of follows from standard Johnson-bound type arguments. If I switch the expectation and the maximum, then everything would be fine. Right? Of course, it's generally and importantly illegal to switch expectations and maxima. So that's not going to work, or that's not going to be enough on its own. So then the meat of the proof is showing sort of a worst case deviation bound like this. So I want to show that with high probability over the worst set lambda, the deviation of this random variable from its expectation is not very large. And that needs to be uniform. I can't switch that expectation to that max.
So lambda is a set of code words?
Lambda is a set of code words of size L plus 1. Right. Or I might elide it into being size L because constants. But yeah.
So you would just use lambda would be fixed in that it would be just some subset of the original code you are going to puncture. So you just need
Right. Yeah. So
sense of pairwise distance between the Z plus 1.
that's right. Yeah. So lambda is some fixed set of indices. So yeah, you could think of it as a fixed set of messages or a fixed set of code words in the original code. Doesn't matter. Right. But I want to take the worst possible set of such code words, and then the expectation is over which symbols I choose to keep. And so, right, these pluralities are random, and they depend on which symbols I chose to keep.
Yeah, there's no need for union bound overlap.
There is a need for union bound.
There is a need for
Right, that's kind of important. Right, that's sort of the whole issue, is that I need this deviation to be small simultaneously for all of the lambdas with high probability. Right. Yeah, so this is what we're going to try to show. Okay, so let's delve into that. And right, so we're going to first try to take a union bound. Right, so the whole game is to show that this is small with high probability, and that's sort of the basic trade-off. But when n is large, I get more concentration of these random variables, which will help us show that it is small compared to n. On the other hand, if n is small, then the code has better rate, and so I want to find the biggest n, the smallest n possible, so that this is still small enough. Right. And so like you said, the first thing you'd try is, well, let's take a union bound. I have here a sum of a bunch of independent mean zero things. I want to show that the sum is small with high probability. Okay. So I know that things concentrate, so let's see how good they are. The problem is that this actually doesn't work because each of these guys, these summands, are not themselves particularly well concentrated because the code words aren't independent. Right, so in expectation they're good, but there might be just some symbols which just all of a sudden are very heavy, just sporadically. And so a union bound, it turns out, does not work. It's not. This is somewhat concentrated, but it's not nearly concentrated enough to allow for a union bound over n choose L things, which is the number of sets lambda that we would need to union bound over.
So just remember,
Yeah.
the randomness here is the choice of the n rows.
That's right.
Yeah.
Yeah. So yeah, these pluralities. I should probably change notation to make this more explicit. The pluralities themselves depend on which of the n rows I chose, and so that's where the randomness is. So here's the basic idea. So a union bound doesn't work, but a union bound is incredibly wasteful for the following reason. So suppose that I have two sets lambda of code words. So let's say I take this set here and this set here, which overlaps with it a lot. And I look at those pluralities, the pluralities of each row. So again, these are random variables which depend on the choice of rows that I took. So here I've written down the pluralities for this particular case. And you can see that these random variables are incredibly correlated, right? Like, they're very. I can't show correlation from one draw, but you can see that.
They have very similar W's, for example.
Right. So they have very similar W's. Yeah, and so moreover, like the number of green symbols in this guy is very similar to the number of green symbols in this guy, and the number of yellow symbols in this guy is very similar to the number of yellow symbols in that guy, and so on. So if these guys overlap a lot, then I expect these pluralities to be very close, and I shouldn't be union bounding over them as though they were totally unrelated. And that's the main intuition, so there's a lot of structure there. So formally what we do is we pass to a Gaussian process, like you suggested, and reason about that. That gets kind of technical, so I'm actually going to give you an overview without mentioning Gaussians. Of sort of what is going on. So the basic idea is that we're going to do a chaining argument. And so we want to union bound over all sets lambda that look like this. So let's say this has size L. And so what we're going to do, and right, we want to say that the pluralities of all of these rows are reasonably well behaved. And the basic idea is to say, well, okay, so here's my set of lambda. Let's fix a set of size L over 2, a subset of lambda, and consider the pluralities in this row, in this set versus the pluralities in this set. And those should be the same, basically, up to normalization. Like the fraction of green guys in this row is, in expectation, the same as the fraction of green guys in this row. And so the expectation over the rows that I'm taking. So just like fix a bunch of code words in my big code, and then fix a subset of those code words, and now take some random columns, right? So in expectation, and condition on, let's say, the number of green guys that show up in the big set. In expectation, the number of green guys that show up in the smaller set is the number of green guys that showed up in the bigger set divided by 2, if I have some fixed set of size 2.
So is it a one coordinate argument, right? You do one coordinate by coordinate. Let's argue about one coordinate, and later you say how many, the sum of how many do I need, so that I'll have concentration.
Yes, I'm going to have to make that argument several times on top of itself. Here, but yeah, essentially, right, I need the independence crucially coordinate by coordinate to get concentration, yeah. So the basic idea is that so the relative pluralities here in expectation are the same as the relative pluralities here, and if L is big enough, then because of concentration, these are reasonably, I can really expect them to be very close to each other with very high probability. And then I can do this argument again. I can divide by 2 again, and I get the same thing. I have slightly less concentration now because these sizes are slightly smaller, but I still expect those to be the same. And again, down to the next level. So
you don't really go to 1, you go to some.
Right. So actually we do go to 1, but with some caveats. So let me flip the slide and answer your question. Yeah. So this is a very informal overview of the argument. So I'm glossing over tons of details, and in particular, I'm glossing over the source of the randomness because in our argument there are some Gaussians, and I'm just like not mentioning them. Okay. But the basic idea of the chaining argument is that okay, so that works here. Like I want to show that this guy is well behaved. I know that this guy is close to this guy is close to this guy, this guy is close to this guy, and then this guy is well behaved because it's so small. I understand how the small guy works.
The union bounds are easier.
Yeah, the union bounds are easier lower down. And there's a trade-off too, because now I had better concentration. When I say is close to, I had better concentration for is close to up here than I had here, and better concentration here than I had here. And when I want to do the union bound, I have more guys to union bound over up here because there are more sets of size L, but the concentration is better. And then I have slightly fewer guys to union bound over here. There are fewer sets of size L over 2. Concentration is kind of medium. And then all the way down at the bottom, I have very few guys to union bound over. The concentration is kind of crappy. And if you do it right, it'll all balance out. And so that's the basic idea of a chaining argument, and that's what we do here. So we can afford to union bound over lots of those green edges, over many of the orange edges, and over a couple of the red edges. And in the favorable case, one would hope everything kind of balances out, and you get that this sort of worst case deviation that we wanted to control is about the same as that quantity when the list sizes are 1. And we would hope that we understand that. So that's kind of a lie. It doesn't really work.
Yeah, but when it's 1, exactly the pluralities are exactly the vector.
Right.
They're all 1.
Yeah, exactly. So when it's 1, you know that the pluralities are actually all 1. And that's actually bad, right? They're 100%. Right? So at some point, this argument breaks down. And in fact, what I wrote on the previous slide was just a lie, right? Because if I have something like this where the pluralities are all 1, so once lambda gets down to like the size of the alphabet, let's say, then I should expect that when I cut lambda in half, that right, the pluralities don't change. They're all the same. And so the fractional probabilities get bigger if I'm normalizing by the size of my set, which is what I was doing. Here the plurality is an eighth, and here it's a fourth, and so on. And so I was trying to argue that these guys would stay the same at this level, stay the same when I do this, but actually they're doubling each time, which is kind of the opposite of staying the same in many cases. So that's not good. But in our case, it's actually okay, right? Because eventually what we wanted to show is that these pluralities were small. And the argument that I said, it turns out basically works until this point. And when does this point happen? This point happens when the pluralities are small. So you can sort of make a trade-off and say that you can run an argument similar to the chaining argument that I tried to do before and stop it appropriately. And you need to take a little bit of care with that. You need to stop it at different points for different sets and for different rows and things like that. But with all the bookkeeping, something like that does work out. And that's basically what we do. And from that, we can show this thing down here, that this concentration is sort of uniformly small.
You run the argument, you don't go to the same level in different branches of this, so it depends on the actual sets of vectors together.
Yes, yeah. Right, and to describe that more would involve describing how the Gaussians come into it, so I don't want to do that here, but we can take it offline if you want. Yeah. Yeah, the chains are of different lengths. Not that I know of. There's some similar arguments in sort of the geometric functional analysis literature by like Reedsolomon and Verschinen and things like that have some similar arguments, but I actually don't know any arguments where you sort of have to stop the chains at different lengths. So that's new. It might be, though. I haven't done an exhaustive search. Yeah, and so using an argument like that, we're sort of able to show that this concentration is good. We already waved our hands about how if I switch the expectation in the max, that was good. And that will show us, together that's enough to show that the sum in expectation, the worst case over lambda, this sort of average agreement is small. That was enough to show average radius list decodability, which is enough to show list decodability. So that's the thread of the argument. And again, here's the restatement. And that's enough to show that if I take a code like this, randomly puncture it, then I get a theorem like this. This is the same theorem that I showed you before. And when you work out what that n has to be in order to be large enough to get the concentration to work out at these steps, n has to be so that the rate is like this. So are there any questions about sort of that kind of hand-wavy overview? I understand there are a lot of details that I didn't talk about. OK, so I was told that the time is informal and loose. How informal and loose is that? OK. Yeah, this is like 10 minutes. OK, so I've got 5 minutes left, and I'll take 10 minutes, and I won't be offended if anyone walks out. But I want to give you a much simpler argument, which I can actually give it its entirety with all the details for the q=2 case. It's actually a lot easier to control this process, and I will show you how the Gaussians come into it there. OK, so let's rewind. So we're going to do the same type of argument. Let's say we've already done this step, and now we want to control this step. OK, so a different argument for the concentration. So we don't know how to do that yet. OK, so there's two tools that I'm going to use. One is a tool called Symmetrization, and one is a notion of Gaussian mean width. So I'll just sort of quickly review these. Probably a lot of you are familiar with them. But so the basic idea of symmetrization trick is, or of this particular symmetrization trick, is that if I've got a bunch of independent random variables yi, I sort of center them and sum them up, and I ask how big their sum is in my favorite norm. Then it is the case that in expectation how big their sum is not much bigger than if I had just put random sign flips in front of the yi's. And I can actually prove this for you in like 2 lines. So let yi primes be independent copies of the yi's. So I take this thing here, put it there, and I'm going to replace yi with yi prime here. Doesn't change anything because of the expectation. Jensen's inequality pulls out the expectation. And now these guys are sort of legitimately symmetric random variables, so I'm not going to change anything if I put in some random sign flips. Right. And then triangle inequality will just give me this. And a similarly short argument will show you that if I want to not have random sign flips here but have Gaussians, I can do that also, changing this constant. Maybe there's like a root 2 over pi or something. Okay, so I now have this theorem that if I've got a sum of symmetric independent random variables, then basically that's the same as if I sort of didn't center them but put Gaussians there in front. No, I think the constant should be like the square root of 2 over pi no matter what. It's the same trick again, right? So instead, put plus minus 1, and then I'm going to divide and multiply by the square root of 2 over pi, which is the expected value of the absolute value of the Gaussian. Pull out the expectation for Jensen's inequality. But for this particular proof, the constants are so far gone, I'm not even going to think about it. But yeah, so there is a constant there. Okay, and the next notion that I'll need is the notion of Gaussian mean width. And so this is the sort of a geometric quantity for a set. So suppose that I have a set T, it lives in Rn. Here it is. Then the mean width is defined this way. It's the expected value of the maximum over all vectors in T of the standard inner product between a Gaussian random vector and T. And so the reason that's called the mean width is sort of this picture. If I take a random Gaussian vector, like basically I'm picking a random direction. So here's my random direction. And then what is the vector little t and big T that maximizes this inner product? It's this one. It's the one that has the biggest projection onto that direction. Okay, so I'm basically, and then I'm measuring how big is that projection. So what I'm doing is I'm taking, or I should draw it. How big is that projection? Right there, this length. And so what is this quantity? I'm taking a random direction, measuring how fat the set is in that direction, and I'm averaging over all of the directions in expectation. So it's like the average fatness, or the mean width of this set. Okay, so those are the only two tools that I need. Okay, so now let's get back to this question. I wanted to show that this thing was small, this maximum of the sum of random variables. And I'm going to do it in like 3 lines of linear algebra. Although it will involve slightly more lines to set it up. So suppose that I'm going to take that picture, that cartoon of a code that I had before with all the code words. I'm just going to shove them together and call it a matrix. So now I have a matrix. It's capital N by little n. All of the columns correspond to code words. And let's say that q equals 2. And so my alphabet is blue and yellow. So basketball season, go blue. Then I'm going to treat these as plus minus 1s. And then I ask, OK, what happens when I multiply this matrix by the indicator vector for a set lambda? So I get a vector, and what is that vector? Well, it's not hard to see that what you get here, right, it's the number of plus 1s minus the number of minus 1s in lambda, which has some relation to the plurality. It turns out that relationship is this. So the pluralities is, if you move the factors of 2 around and add it up, you get that the plurality has something to do with the absolute value of this entry. Yeah, it's the majority. So you need to divide by 2 or something because you're minusing and subtracting. But basically, what it comes down to, if I want to control these sums of the pluralities, I just want to control the absolute values of the elements of this matrix vector product. Right? So this thing turns into this thing. I want to show that the L1 norm of this matrix vector product is small, or is close to its expectation. Okay. And now this is something that we know how to do, right? It's showing that these things are concentrated. So to control this concentration, I'll just do it out. So here's the thing I want to control. I'm going to write out what the L1 norm is. So it's a sum of the absolute values of inner products. But now these are independent centered random variables, so I can use that symmetrization trick. So now I'm going to introduce some Gaussians. And now I'm just going to relabel. Instead of taking the maximum, I skipped a step. I was taking the maximum over all indicator vectors, and I switched to taking all vectors of L1 norm L. So it's only going to make things bigger. And now instead of taking, and so here I've just rewritten this. And now instead of taking the maximum over all vectors of L1 norm L, I can take the maximum over all vectors in this image of the L1 ball, right? So I'm looking at all y's that live in A times the L1 ball of the inner product of G and Y. And that's, we just saw that is the mean width of this sort of translated L1 ball. So, and it's sort of, no, not translated, sorry, some linear map of this L1 ball, and the linear map is precisely that matrix A that I wrote down, this matrix full of plus minus ones corresponding to the code. I don't, actually.
That was your assumption about the code, no?
Yeah, so the distance I used, there we go. I used distance here.
That's the only place.
That's the only place, and here I,
Concentration, you don't need it.
yeah, for concentration you don't need it at all. Yeah, so actually I'm not going to use the distance of the code. I'm just going to use sort of easy stuff, right? So I have this L1 ball. I take A of it. I get something. I don't know what that something is, but I know it's the convex hull of the columns of A, right? And now this quantity that I was after, this mean width of this guy, it's not hard to see that the mean width doesn't care about taking convex hulls. So I can just take basically the maximum over all of these vertices, the columns of A, and their opposites of this random variable. So, but what is that? That's a Gaussian random variable. It's normal with standard deviation square root of n, or with variance n, which is just the L2 norm of the columns, which are all plus minus ones. Right? And so that's the maximum of 2n Gaussians with variance little n. Okay. I know what that is. It's like square root of n log n, more or less. And so, right, we wanted to show that this thing was small. Now it's small. And it turns out that that level of small is enough to show a statement like this. And that argument can work for larger Q, too. It just doesn't get the right dependence on Q as Q gets big. But you can take that simple argument shows that you can get rate something like epsilon squared over log Q. And you get list decodability sort of up to the desired bound with the right list sizes. So the problem here is that you don't get the right dependence on Q. There should be a Q upstairs. And so that gets the result that I claimed for binary random linear codes, or for random linear codes over constant-sized alphabets. So that's the whole proof. Are there any questions about that?
Yeah, you didn't actually have to use the generic chaining argument.
No. Yeah. So this is like totally elementary, nothing fancy. Right. I guess implicitly, whenever you talk about mean widths, there's like a generic, like if you wanted to be pedantic, you could say that I know by majorizing measures that that's equal to some generic chaining, but right, I'm not using that. Yeah. Okay. Yeah. So let me just quickly conclude. So the point of this talk, or the main motivating question was, are there Reedsolomon codes which are list decodable beyond the Johnson bound? The answer was yes. Sort of another point was about random linear codes. The answer is also yes there. Right, yeah, so the result is more general, gives improved bounds for random linear codes, randomly punctured codes in general. There are still a lot of open questions, so the thing that's like the obvious open question is to remove the log factors. The factor of log Q is like especially obnoxious in the case of Reedsolomon codes for the desired punchline. Another interesting question is actually finding a Reedsolomon code which is optimally list decodable, right? So you asked about the efficiency of decoding, and that's like definitely not going to happen. But can we even, this is a really non-constructive result, can we even find such a code efficiently? Or I think it's a really interesting question to find sufficient conditions on such a code, something that sort of smells like the Johnson bound. Right, so those counterexamples for Reedsolomon codes, the evaluation points all had like certain algebraic structure. So maybe you could make a statement like if you have a Reedsolomon code of such and such a rate where the evaluation points lack this algebraic structure, maybe you take them to be a subspace of basis set or something, or I don't know, then you could get good list decodability, and that would be really cool. And finally, one thing I'm interested in is trying to apply this type of argument to other pseudorandom objects. So list decodable codes are related to extractors and expanders and sort of all your favorite pseudorandom gizmos. And so if any of you have open problems about pseudorandom objects, I'd love to know about them. Okay, so that's all. Thanks.